Okay, the next two examples we're going to look at are going to involve filling tanks. So we got this example 2. And basically they say water pours into a fish tank. So water pours into a fish tank at a rate of 0.3 cubic meters per minute. You want to say how fast is the water level rising? How fast is the water level rising? If the base of the rectangle is 2 by 3 meters. So basically we got a box here that's 2 by 3. If we make that 3, that's 2. You have kind of some water level in there that is at a height of h. And water is going into this. Water's pouring into there at 0.3 cubic meters per minute. So we're going to use the volume equation. Volume of this would be length times width times height. So length times width times height. Since if we think about the way the water is, the tank length and the tank width, they're always 3 by 2. The tank, as you move up on the tank, it always has a 3 by 2 cross section. So the length and the width don't change with respect to time, only the height does. So what this means is we can treat the length and width as constant. So we can say the volume is length is 2, length is 3, width is 2, so it's 6h. And this is the equation we will take the derivative of. If the if this thing had if the length and width were changing, like maybe you had a tank where it was getting bigger as the water increases, then we'd have to treat all of them as functions, and the chain rule would apply to all of them. But the way that the problem is, for this one at least, the length and the width, if you move up the tank, it's still 2 units wide, 3 units long. If you move up further, it's still 3 units long, 2 units wide. So we're able to just view those as a constant. So basically what we end up with is dv dt equals 6dh dt. That's our equation. So what's asking us, the problem's asking us how fast is the water level rising? See, am I missing a value here? Nope, it says how fast is the water level rising if the base is that. So it's asking us what's the dH dt. So I'm going to take the 6 and bring it across as a 1/6. So 1/6 dv dt is dH dt. And dH dt is what the problem's asking us. That's the rate that the water level, the rate the height is changing, which is the rate the water level changes. dv dt, that's the rate the volume enters, so that's 0.3 cubic meters per minute. So we get 1/6 times 0.3 is the rate the height changes. So 1/6 times 0.3 ends up being 0.05. The units on AP test are always going to want units on problems like this. If the water is entering at cubic meters per minute and height is just meters, this rate will be meters per minute. So it's rising at a rate of 0.05 meters per minute. Okay, so that one's pretty easy. A lot of what made that one not too bad was that the tank profile stayed 2 by 3 as you went up, which meant that the length and the width weren't changing with respect to time. So we were able to just kind of view them as a constant. The next problem is going to be a little bit different. It's going to have a conical tank, which means that the length and the width as you go up the tank, they do change, and that's going to cause stuff to be a little bit trickier. So we're going to have water pours into a canonical tank of height 10 meters and a radius of 4 meters. At a rate of 6 cubic meters per minute. Part A, at what rate is the water level rising when the level is 5 meters high? So at what rate is the water level rising when the level is 5 meters high? And part B, as time passes, what happens to the rate at which the water level rises? Okay, so we got some sort of cone tank here that's something like that. They're telling us the tank is 10 meters tall and it has a radius of 6. And we're going to note also we could say that there is a height h here and we have a radius of r here. We're going to need that to kind of link some stuff together. So this just says if you're at an arbitrary height in the tank, there's an arbitrary rate, or there's going to be a radius that depends on what height you're at. And unlike the previous fish tank, as the height gets taller, the radius gets bigger. So in this tank here, the radius is changing as the water level increases. And we're kind of viewing the height as its own variable because it's going to eventually ask us what rate is the water level changing when the height is 5 meters. So for part A, we're going to start out with the volume of a cone because they told us water's pouring in at 6 cubic meters per minute. So we have water's coming into the tank at 6 cubic meters per minute. And that's going to slowly fill the tank up. That's a volume, or it's actually rate of volume, so it's dV dt, the rate that the volume changes per minute. It's asking us, in part A, it's asking us what rate is the water level rising. That's asking us what is dH dt. How is the height of the water level changing with respect to time? The problem here is the radius also changes with respect to time. As the tank gets higher, the radius gets bigger. So we're going to start out with the volume of a tank, which volume is 1/3 pi r squared h. This is the volume of a cone. So the first thing we need to do, we have v here as a variable, or it's the function name. We have r as the radius variable and h as the height. We need to somehow get this all in terms of just one variable. So I'm going to use similar triangles, and we're going to say if you kind of look at the side profile of this tank, there's a big triangle that's 10 by 6 because the height is 10, the length is 6, so we can kind of view a triangle here that's 10 by 6. And then there's a smaller triangle, a similar triangle in there, that's h by r. So if we use similar triangles, we can say radius over the height equals the radius of the tank over the height of the tank. And then if we want to solve this for r, we can say that this as the radius is, 6 over pi reduces down to 3 over 5. So it's 3/5 times h. So the radius is equal to 3/5 h, so I can plug that in for the radius here, in this equation and get that the volume is 1/3 pi times 3/5 times h whole thing squared times h. So now what I need to do is I need to simplify this. So volume is 1/3 pi. I'm going to square. Let me scoot over here. Have the lights turned back on. Going to square all the values inside the stuff squared. So 3 squared is 9. 5 squared is 25. H squared is h squared. And then that's times an h. We have a 3 down here and a 9 up here. The 3 can cancel into the 9. That'll leave a 3 there. So we get volume is 3/25 times pi times h cubed. So still all part A. We're just trying to, all the work we're doing here, we use similar triangles to replace R with H. And so since we did that, we can, well, let me pause it here real quick till passing period's over.